Thank you. We're into the final session of wonderful 2 days. I'll be back a bit later on, maybe to share some very briefly a few thoughts on what's been a really provocative event. My job right now is just to simply introduce Kathrin Dörfler, who will be leading this final session for us, and she'll be starting out with an opening statement to put it into context for all of you. Just to put who Kathrin is into some context, there's a wonderful connection between Kathrin's career and FABRICATE, if I might borrow that kind of relationship a bit for a moment. She's an architect, researcher, and educator in computational design and robotic fabrication, and her academic career has got going since the early part of the 21st century. So in around 2004, I believe, she started in the Angewandte in Vienna, went to the Technical University, so switched from that shift from the avant-garde to the technical in that cauldron in Central Europe of industry and arts and human endeavor. I think there's an incredibly strong culture that we can talk about in terms of where people are coming from. So there's some wonderful words today about we and I think the centers of excellence and learning that are represented in this space today. And also for those that are not here, it's incredibly important to recognize. So having done her undergrad and postgrad education in Vienna, Kathrin moves to Zurich, that other great center of research and excellence in this space, and starts her PhD in 2013, the year before we had our second FABRICATE in Zurich. So there's a really wonderful kind of connection there, which I could borrow too. And participated in that acceleration of inquiry into robotics and fabrication that Gramazzi and Kohler kind of kicked off with their wonderful work, and developed her own thesis around strategies for robotics in situ fabrication, which is something which will be teased out, I'm sure, no doubt, in the discussions that are on their way. And then she moves to the Technical University of Munich as a professor and sets up a research group which so happens to be almost exactly between Zurich and Vienna. So there's something going on here, that she's moving from Vienna to Zurich and back to somewhere in the middle. There's something going on there in that conversation, in that relationship, which we might tease out of her too. But as somebody who has contributed enormous amounts in different ways, as a young researcher, as someone now who's a professor, who's contributed to 2 papers, one this year and one in 2020, and is also leading a research group in her own university in Munich, and is also the co-spokesperson for a collaborative research center in additive manufacturing and construction in collaboration with Braunschweig. Please welcome Professor Dr. Kathrin Dörfler.
Thank you so much for this very nice introduction. I'm very honored to welcome you to this last session, Rationalize Elements and Assembly, and I'm really honored to panel the session with 4 speakers that I, for some reason, all personally know. I will not go into details on that, but we kind of share similar pasts. What they will present mostly is about assemblies, like how do parts come together, and we will learn about how buildings can be discretized into parts, prefabricated and then assembled on site. So taking the complexity into the prefabrication part and taking it off the site. Highly influenced, or basically this kit of parts idea, which basically comes from timber fabrication, and basically means that you design, you prefabricate parts, you manufacture them, highly customized components for on-site assembly. And recently this has also been sort of brought to mineral materials, to concrete construction, or to other fabrication routines, such as, which we will see by Christoph, fiber winding or robotic fiber winding. In the end, the idea is to have structurally optimized or functionally optimized components, which are highly individualized But it's not just about the parts, but the question is also how these parts come together. And a recurring theme in all of your presentations, and I think this will also then later come into the discussion, is not just how do they come together, but how do we take them apart again. So this question of or design for assembly and also design for disassembly. So preferably with mechanical connectors so that they are able to be disassembled later. And then also in view of material separability, I think this is a topic which we also should discuss later on in the panel discussion. In here, nicely shown with post-tensioning systems such that the tension and compression members are separated, such that it then can be taken apart later on and where it's easier to recycle. But this question of customization, individualization versus standardization is something I think that we have been discussing recurringly, and that should also inspire our discussion later. Having said that, short sneak peek of some detailed photos, I will now like to give the stage to the presenters, and we start with Christoph Zechmeister. I know Christoph Zechmeister from Vienna, but he also studied in Vienna, and he's now finished his doctoral thesis already. He is a senior group research leader, I was told, at the ICD Stuttgart, and I'm happy that you will show us the beautiful Livmats Pavilion, part of your thesis, I understood as well. Thank you.
Yes, hello, thank you so much for the invitation. It's a great pleasure to be here and to have this opportunity to share a little slice of our work that we do at ICD and ITKE in Stuttgart on computational fiber architecture. I will be presenting our paper today, the co-design of natural fiber composite building elements by the example of the Livmats Pavilion on behalf of our multidisciplinary author team. The Livmats Pavilion is a shell structure that is made of 15 natural fiber composite building components. It demonstrates the first application of coreless filament winding using a natural fiber system with the aim to establish a load-bearing structure that is completely made of flax fiber components. So the pavilion is located in Freiburg in southern Germany at the botanical garden there of the university. It was designed by ICD and ITKE at the University of Stuttgart together with a team of ITech master students. Many of them are here today also, which I think is fantastic. And it was produced and assembled by the industry partner of the project, Fiber. So before I get into the component development, I think it's good to give a bit of a background to see why we're even attempting to build or to make building components with fibers. So if we look at the bigger picture in the construction industry today, then we can see that there has been a lot of digital progression recently. However, the construction industry is slower to adopt this digital innovation. However, it would be important because there's a significant global requirement for additional floor space that we will have to build over the next years, and we've discussed this before also yesterday. So that's going to be a challenge to achieve and will require initial or additional effectivity in construction. And on top of that, there is, of course, the climate crisis, to which construction is also significantly contributing with about 37% of global energy and process emissions coming from the construction sector. So I think the question becomes that we should ask ourselves as architects, what can we do differently? How can we build differently? How can we be more effective and at the same time more sustainable? And for this problem, we can find a lot of inspiration in natural systems. So if we look at how nature works, then we can see that we have a very high degree of integration of form, material, and structure. And nature achieves material savings through differentiation and geometric complexity. And if we look at the current state in the construction industry, that's is a very big contrast to that, because we're mostly prioritizing uniform building components to mass produce them, right? And this integration, or this principle of integration, does not only apply to natural systems, but we can also transform that to technical fiber assemblies. And leveraging this potential is strongly tied to the way how we fabricate these assemblies. And a very interesting technique from the industry is filament winding. So basically here, resin-impregnated fibers are deposited on a mandrel in different pattern formations. And by changing this pattern, we can customize the performance, and we can tailor the material placement to our needs. And that's also very interesting for building components. And based on this principle, ICT and ITKE developed coreless filament winding throughout the last decade. So basically that's enables the production of morphologically differentiated building parts with minimal formwork. Here we have resin-impregnated fibers that are deposited around anchor points on winding frames to create highly customizable and multi-layered fiber components. And the shape of the composite is established by the interaction of the fibers. And this enabled the production of a series of demonstrated projects throughout the last years. They demonstrate how we can create lightweight, highly performative composite components. However, if you look at the material system, they use carbon and glass fibers. And these materials, they are based on non-renewable material sources. And they consume rather high, or they have rather high global warming potential and embodied energy. But we can improve on that. We can change this material and use plant fibers instead. So if we look at flax fibers, they have high stiffness and strength values, and they can be locally grown in Central Europe, and they don't depend on non-renewable energy in the production, and they don't have, so they don't depend on petrochemical sources. Yeah, that's the base material. So the raw material consists of fiber filaments, either parallel or slightly twisted, and they are impregnated with a resin matrix that acts as a binder. And these fiber bundles are anisotropic, so that means the longitudinal direction has a much higher stiffness than the transversal one. And that's an important precondition for our fiber formations, because we can leverage this fact. So we can tailor the composite and the stiffness and the strength to the direction and the magnitude of the loads that we have in our structures. And to leverage this potential of anisotropic fiber formations, we developed a feedback-based co-design workflow that is represented as 4 iterative cycles. It relies on concurrent information exchange, and it allows for the co-evolution of computational design, structural engineering, and robotic fabrication. And the use of plant fibers now adds additional complexities to this process, because the fibers, they have higher variabilities in their mechanical properties, and we need to account for that also in the design process. So basically, all those development cycles need to be extended. So the material system has a significant influence on the design boundaries. It impacts component dimensions, span, connection amount, connection type. And the characterization of the material becomes really important. So here we use small-scale specimens to determine the actual mechanical properties that we can get out of these material systems with our fabrication system. In the next step, this has to be evaluated, basically the scalability of those small-scale investigations at a full scale through full-scale prototyping, which is very important for the fiber layer development. And ultimately, we want to optimize our fiber patterns to make sure we use our material system to its maximum capacity, so we find the boundaries of this material system. Throughout the component development, our computational models are continuously informed and calibrated by real-world feedback that we derive from small-scale prototyping, full-scale prototyping, and subsequent structural testing. Especially prototyping at the full scale is important. because it gives us feedback on the manufacturing feasibility, structural integrity, and also the design quality. And the subsequent structural testing allows us to calibrate digital models and to determine safety factors for all of our fiber patterns. The development of the component started with the exploration of the design boundaries. So here the material capacity was estimated in preliminary structural investigations and models to allow for like a maximum of 5 meter span. So that led these initial investigations on the component morphologies that we can see here. And we ended up with a global design of 15 components that are radially arranged in three groups of 5 component types each. And the center is closed with like a triangular keystone element, and then we have a polycarbonate skin to cover the structure and to shelter the interior and also protect the natural fiber components. The final anchor point configuration looks like this. So basically we have 2 curved segments and lateral edge anchors that define the component. So this the component can be divided into 2 surfaces. We have like a front and a back surface. And the front surface is conceived as a lattice-like layer, and the back part of the component is composed of multiple truss-like layers, and it supports the polycarbonate skin. Each fiber component is about 5 meters long. And here we can see the individual layers that make up the 2 surfaces. So we see the back surface that's composed of multiple truss layers and then additional bracing layers to push fibers together to improve fiber interaction. And this back part receives and distributes the snow and wind forces that act on this polycarbonate skin. And the front surface makes use of the high surface curvature that we have in this part for increased fiber interaction of these long spanning fibers. It's a combination of scaffolding with longitudinal structural spine and additional corner reinforcement to add additional stiffness and to make sure that we reduce the buckling length. And together, those 2 surfaces, they form a closed hollow section, and that increases geometrical stiffness. So to understand the material, we started material characterization based on what we knew. So we used carbon fibers and petrochemical epoxy and compared it to different flax fiber combinations. So we had flax fibers and petrochemical epoxy and flax fibers and partially bio-based epoxy. And what we saw is that the performance of the carbon fibers is, of course, the highest. With the flax fiber combinations, we reached, then this is in compression, roughly half of that. And we also saw that if you look at sustainability markers like global warming potential and energy intensity, that if we use plant fibers, the fiber contribution is drastically reduced. However, the resin contribution is still pretty high. We can reduce that by about 20% if we use partially bio-based epoxy. However, given the tight time frame of the project, we decided for a combination of flax fibers and conventional petrochemical epoxy. And with the material system in place, the first full-scale prototype could be built. This was done by the students and aimed to evaluate the scalability of the initial material characterization and the preliminary fiber layup. This was as such very successful. However, it showed inconsistent material impregnation, which was because of the fiber product. So we used a fiber roving with a small twist that was pretty hard to impregnate. So we changed that to a flat roving that was easier in terms of impregnation. Again, we had to recharacterize the material, this time using a simpler specimen, just a loop that was investigated in tension and compression. And this then showed improved impregnation, and we could continue. So this is the actual fabrication at the industry partner's premises, where we started to produce pre-series components. In total, we made 3 of them. They were destructively tested, which is important to verify the material system at a full scale. And the FE model of this test setup is then used as a calibration tool to compare physical and digital performance. The results are then integrated into a comprehensive digital model that basically acts as a point of confluence and contains data and information from different domains like design, engineering, and manufacturing. And based on these pre-series components, we could identify further issues. So we again had lower than expected performance in the tests, and also fabrication issues, as you can see here, so sagging fibers that could be reduced, or that could be mitigated basically by adding a different additional material, so a scissor yarn that was embedded in the fibers to take increased tension loads during the winding. And the lack of performance could be traced back again to impregnation issues that this time could be resolved by modifying the manufacturing equipment, so the end effector of the robot and the resin bath. And then again, we retested that, and this is a cross-section through the bundle. So here you can see that was the first iteration, and then this was the final iteration, so we have a much smoother and better impregnation. With those adjustments in place, all 15 components could be successfully produced. Each of the components is about 100 kilograms. It can take compression loads of up to 40 kilonewtons. The components were then assembled. The assembly was a very fast process, so they can easily be handled by a small team with the help of a small crane. They were put in place. And that's the final result. So the entire fiber structure is only 1.5 tons. It covers an area of 46 square meters, and it complies with the German building code and the structural requirements that go with that. That's the interior view, so we can see this kind of unique visual expression of the natural fiber composite elements. Yeah, and summing up, I think we saw that plant fibers can provide ecological benefits over the use of carbon and glass fiber components. However, we also saw that they add additional complexities to design, to manufacturing and evaluation, which we need to account for by flexible and interdisciplinary design workflows that allow for like a material-driven development of these complex fiber patterns. And to wrap up, I want to mention two points that like originated from this process, from this project that we are currently working on. The first one is LCA indicators. So I mentioned that before. So we used the global warming potential and energy intensity to evaluate different materials, but to fully assess the component sustainability, we need to incorporate more comprehensive LCA in the design process. And the other point is the use of the petrochemical resin, which of course was a compromise that we had to do because of the short time frame of the project. And there we are investigating both partially bio-based resin systems, but also fully bio-based resin systems to ultimately produce components that are biodegradable. Yeah. With this, I would like to conclude and thank you for your attention, and I'm happy to answer your question later in the discussions.
Yeah, thank you, Christoph, so much. We have next Anton. I'm very happy to introduce her. She's now a postdoc at DBT, Benjamin Dillenburger's group at ETH, and she's going to present us her newest developments in the Tor ALVA project, a 3D printed tower, and we are happy to hear all the details.
Thank you, Kathrin, for the introduction. It is fantastic to be here and present our work on behalf of all the authors. I am currently a postdoctoral researcher in the group of digital building technologies at ETH Zurich, and my main focus is on upscaling 3D concrete printing for prefabrication scenarios. Tor ALVA project initially emerged from interdisciplinary collaborations within the NCCR digital fabrication, and will be one of the large-scale demonstrators of phase 3, focusing on technology transfer to industry. Tor ALVA in Romansh translates to White Tower. It is a 30-meter tall structure dedicated to the performing arts. This project is designed by Benjamin Dellenberger and Michael Hansmeyer for a real client, the Origin Foundation. The structural engineering is ensured by Consent Bronzini. And we have many industrial partners, from which I want to mention Zindel. As the contractors of the project, they are in charge of assembling all the components on site. But we also work with two spin-off companies from ETH Zurich, Mesh, responsible for doing the interlayer reinforcement, and Saeki for 3D printed formworks. Concrete is an incredibly versatile material, capable of taking any shape if poured into a formwork. The dream of building concrete structures without a formwork is not only a sustainability solution, but it is also a liberation of how we design for this material. These are the beginnings of ETH, but here are the real beginnings. Herschel patented this machine for unreinforced concrete walls in 1941. The unreinforced wall is the most direct translation of a layering process into a building component, and ironically, this remains the most common application of concrete printing in construction. We heard yesterday that from the industry's perspective, it all resolves to cost and time. And this is why most built architectures are productivity-driven. So we see many examples of housing units monolithically 3D printed in situ. Almost all these approaches follow the use of 3D printing as lost formwork, because this is the most direct way to comply with norms and current regulations. And this creates applications with limited structural demand, like this chart shows, with 48% small houses and 16% urban furniture. In this context, it is important to question the direction in which we steer this technology and what are the implications of digital fabrication for the construction site. And in contrast with existing architectural examples, our approach to 3D concrete printing is based on achieving structural integrity with minimal material, printing at high resolution, intricate designs, and produce components in prefabrications for modular construction with dry assembly connections. This slide shows the broad scope of additive manufacturing technologies with concrete. For Toralva, we work with extrusion-based 3D printing, focusing on free-flow extrusion with a two-component material system. Our reinforcement strategies focuses on solutions that are most direct, that have a most direct application in construction. We insert the main reinforcement after 3D printing, either as bonded rebar or as post-tensioning. And the scale of the secondary reinforcement is closer to that of the layer, making the two processes compatible, especially in our chosen solution of placing the shear reinforcement between the layers. The first implementation of this process is based on using a large batch of retarded Portland cement mix that is prepared in sufficient quantity for the entire print. This material is then later on intermixed with the accelerator, the nozzle, and it enables a very fast vertical build-up rate, especially suited for columns. The 3D printing system, this 3D printing system was tested at large scale in the first collaboration we had with Origin Foundation, where we designed and built an outdoor installations of 9 bespoke columns to set the stage for the 2019 edition of the Origin Festival of Culture. The columns share a similar typology with an outer ornamented shell and an inner vertical core. The core is reinforced with a rebar cage and cast concrete. In this route of innovation, the 3D printing was purely lost formwork. As the collaboration with Origin Foundation expanded in scope and vision, this also led to new architectural opportunities, like the tower. This multi-story building uses the 3D printed concrete structurally and is designed to comply with the Swiss building codes. One main design requirement given by the client was that the construction should be a modular tower suitable for disassembly. Being able to produce this tower also meant adapting the fabrication setup for longer production cycles. We implemented a dry mixing system by preparing the material on demand, just adding water to the dry powder. Next, we also wanted a higher control of the filament properties, so we can extend the capacity of overhangs, but also to really control the material-driven ornamentation. The dry mist system was tested on the fabrication of the first demonstrator for Tor ALVA, and you can see here how hollow shell elements are printed to up to 2.5 meter high, and they will be assembled into a 4 meter tall structure. In this iteration, the columns are still vertical and assembled from 2 3D printed components fitted with a conventional rebar cage. This time the columns are hollow. They are transported on site and handled with regular construction equipment, where they are assembled using 4 post-tensioning rods driven through the middle of the column. For the demonstrator, the building system consists of discrete columns and slabs, where the dry connections are fitted with shear keys. Because joining 3D printed components directly, it's not a very aesthetic solution. We opted for treating the joint with this intermediary cast concrete to create an alternation between the components that are assembled on site. And this prototyping session helped us understand the main challenges of the project. So we really had to think of how we can improve and go from a printed material that was not considered load-bearing to a new design. We also wanted to change the pillars from being vertical and reduce the number of post-tensioning tendons in the core. And we also wanted to have a better solution for joining the 3D printed components. The redesign introduced branching columns with a variation from 2 to 4 branches. And this V-column arrangement also increased the structural performance of the elements to resist horizontal forces better, where one of the branch acts in compression and the other one in tension. As we progress, the columns gradually get slender until we reach the last level of the column under the cupola, where the performing arts space is planned. Transitioning from vertical to branching columns allowed for a rationalization of the building system into 32 self-similar components, discretized following the structural logic. The columns not only act as structural elements, but are also central space-defining feature of the tower. Each component is further discretized for fabrication constraints into a cast base, a Y3D printed element of 2 meters, a continuation of the branches, and the precast capital that closes the assembly into a structurally rigid component. As far, we experienced that casting the bases poses more complexities than actually 3D printing the columns. The component is finalized after vertical rebar is placed and grouted into the hollow channels of the structure, and each branch is post-tensioned with one rod that crosses between the 2 elements. The redesign of the columns from vertical to branching reduced also the number of post-tensioning elements per branch. Our print path rationalization is based on a 3-layer approach in which the outer layer stays visible and integrates the ornamentation. The middle layer hosts the interlayer rebar, and the inner one creates hollow channels that host the main reinforcement that is grouted within the element. Initially, we wanted to design hyperbolic cores. However, we were not able to reliably grout this intricate network of channels and make sure that the bond with the vertical rebar is ensured. The power of procedural design for print path generation is shown at the intersection of 2 branches. Unlike entirely hollow elements, we maintain the logic of the branch into this intersection by overlapping the path. In this way, the flow of forces is not interrupted. And we are also able to solve the placing of the horizontal rebar in different layers, keeping the simple circle intact. From a structural design perspective, placing the layers perpendicular to the main direction of the branch is ideal. However, it's not so easy from the assembly perspective. So we decided to balance the structural design with the practicability of construction and use these inclined layers only in the cupola section. We achieve a seamless visual link between individual 3D printed elements through material-driven ornamentation. This natural drip of the material during printing creates the interlocking effect that slightly hides the seam. We implement this by using as printing substrate the 5 previous layers of the components that we separate with a thin membrane. This type of connection is not high resolution in a geometrical sense, but is inspired by how repeatable the process is. We tested the structural concept on 2 specimens, 2-meter tall V columns. One of them was fully reinforced, the other one had also post-tension. Additionally to the reinforcement, both columns exhibited a ductile behavior. And the successful tests allowed us to eliminate the post-tensioning rods in columns spanning level 1 to 3. Level 4, in which the columns measure 6 meters, will include both reinforcement and post-tensioning. And the cupola, where the columns are 3D printed with the layers normal to the main inclination, there will be no reinforcement, only the post-tensioning going to the middle of the columns. We continued production of the elements. This is an image of the production space. We scan the elements to build a database of the projects, and the overall shape is very accurate. The only deviations occur in the material-driven ornamentation, which is, of course, on purpose. The columns are picked up with a regular crane and delivered to the prefabrication company for assembly. I want to mention that this is a highly interdisciplinary project, and we have many partners and collaborators. And this brings me to the conclusions of my talk. The projects highlighted here exemplify points along several years of interdisciplinary research that aim to use 3D printing of concrete directly as load-bearing material. This research showcases a process that has matured from academia, and it is ready to be applied to architectural scale projects. However, the constructive interactions with the client should not be underestimated. The urgency to produce faster iterations without compromising design integrity, in our case, was a real catalyst for innovation. I also showed that it takes several design iterations to refine this process of designing for a new technology. What I think needs to follow is to get a better understanding of the structural behavior of the material and be more confident to use less of it overall. Another dimension of this work really focuses on design and on the importance of design for creating new structures. It is, first of all, responsible for adding value to our social, to our society, and we should aim to create or to design spaces that can last multiple generations. We also have a huge experience on what it takes to work with different ways of shaping concrete, and it is important to say that being able to produce or to directly 3D print concrete components, it is more economical than prefabricating them with conventional methods. And this is all from my side. Thank you very much for your attention.
Thank you.
Yeah, thank you so much, Anna. I'm sure there will be many questions. Next, we have Masoud. Masoud Akbarzadeh. We share that we both have been ETA fellows at the ETH. You have been ETA fellow with Block Research Group, and now you're a professor at UPenn. And you will present us the 3D printed post-tension concrete canopy. It now has also a name, Diamanti, which I don't have in my notes, but the stage is yours. Thank you.
Appreciate that. Well, thank you very much, Kathrin. It's a great honor to be among you and presenting an ongoing research, which is the result of at least 4 years of collaborative research between academia and our industrial partners, Sika Group Switzerland. And many, many other people actually joined in the way to go. So I'm here on behalf of all the authors to present an ongoing research in the field of concrete 3D printing, particularly post-tension concrete 3D printing that could be recycled and repurposed at the end of the life cycle of a building. So before I start my presentation, I just wanted to acknowledge the fact that among you, there are many individuals who are in the same battle as we are against carbon emission. And I was pleased to see that in the previous presentation, there was also slides about the carbon emission and contribution of construction industry, which is almost 40%, which shows that we are taking actions against reduction of carbon. Among that, I'm particularly interested in this talk about the contribution of reinforced concretes. And you know that cement is responsible for 8%, the production of cement is responsible for almost 8% of the world CO2 emission. And then the embedded reinforcement, which is a steel, has at least 9.2 times more embodied carbon than concrete, well, cement itself. So we have to deal with this conventional reinforced concrete design. But I just wanted to bring your attention to the development that has happened in the past 60 years in the field of design of reinforced concrete. And that is related to development of pre-tensioned and pre-stress and post-tensioned technology in the field of concrete. So for your information, the history of post-tensioning dates back to 1928 to 1938. That was due to the lackage of steel production as a result of World War II. This is really interesting because at the time they actually wanted to deal with lower or fewer embedded reinforcement. And that was the reason that post-tension concrete was developed and practiced and used and researched since then until today. So what do we have today? And just briefly speaking, what is the meaning of post-tensioning for those of you who are not familiar with the topic? So if you take a regular beam under its own self-weight, the internal stress within the beam is actually compression and tension as a result of bending moment in the system. So what happens is that if you apply loads and forces at both ends of the beam, you're changing that internal stress distribution and forcing the entire structure to act as a compression dominant. And that is really key. I mean, similar to the arches that work as compression dominant, post-tension system also works as a compression dominant that allows us to build basically longer spans with fewer material. And there are certain cases that they're showing that post-tension concrete can even reduce the use of concrete by 51%. That is pretty damn efficient. So how do we need to deal with this? How do we compete with them? How do we compete with reinforced concrete, particularly post-tension reinforced concrete? So I just want to bring your attention that, to the point that, yes, it's an efficient system for concrete construction, but it cannot deal with some problems that we are facing for future. And that problem is about recyclability of concrete. The reinforcement is embedded within concrete. That makes the recycling process quite energy intensive. And also, it does not solve the problem of embodied energy as a result of construction method, because it relies on the conventional method, including all the construction waste and formwork. And also, it does not reduce the construction, the emission of concrete itself. So this is our response. So the main intention behind this research is to develop a system that has minimized reinforcement, that the reinforcement is not embedded, so you can easily take it off at the end of the life cycle, and it also has a minimized use of concrete. As you see, it is actually have a very, very minimal amount of concrete in the cross-section. So how do we do this? We start by looking at the design of a funicular system that has both tension and compression combined. So this is actually a very simple 2D graphic statics method that is covered very well in the practice and research previously. The only thing that we do is that we develop a design that has optimized force distribution in the bottom chord, which is actually the tension. The reason for that is that we would like to have constant stress within that member. So in the later stage, we replace that with the reinforcement or the post-tensioning cable. So in the next stage, what we do is to model the effect of post-tensioning in the structure. So if you remember what I showed you in the previous slide, how the post-tensioning result the entire structure to go into compression only by developing a funicular form and adding that curved post-tensioning element into the system and designing that to have constant stress, we would be able to push the funicular system to act as compression dominant. So the next stage is to extend this two-dimensional simple design to 3D. For those of you who are familiar with polyhedral graphic statics, you can extrude this 2D graphic statics to point to get three-dimensional force distribution. And you can visualize that force distribution by combining these form and force diagram into Minkowski operation to see the stress constant design, right? That again, you have control over these three-dimensional curves and the amount of control and the amount of control force and the depth of your structure. But for those of you who are familiar with the funicular design, you know that these structures are designed for a particular loading scenario. That means that if your loading scenario during the lifetime of the structure will change, you may need to take some action in the geometric design to add to the stiffness of the system to take asymmetric loadings or take unpredicted loading during the life cycle. So what we do here, we take advantage of three-dimensional minimal surfaces and embed that three-dimensional minimal surfaces into the system, as you see. So we contort those minimal surfaces to gain additional geometric stiffness for the system. But that's not as easy as you think, because production of this would require dealing with fabrication challenges. So these areas that you see are quite problematic for 3D printing purposes. So what do we do is, before we get into the optimization level, we do a search to see what would be the best type, or at least the type that has minimal amount of overhangs to be dealt with. So we go through a variety of different, we run a search over the variety of different families of triply periodic minimal surfaces, and then we ended up with a diamond surface, and that's, for those of you who are wondering where the name is actually coming up, the Diamante is actually the Italian name for diamond. So we take another major step. We average normals of these triply periodic minimal surfaces. We turn it into polyhedral surfaces because that gives us more control over the geometry and the curvature. And then we go from there and smoothen up and optimize it for overhang and 3D printing process. So if you integrate all this system into a parametric model, you would end up with a boundary condition, the design load, funicular form finding, embedding your triply anticlastic surfaces, adding volumetric geometry to this, and then embedding your reinforcement, which is, again, not grouted. This is just basically reinforcement that goes through the conduit, and you can take it off after the life cycle. And you cut the geometry based on particular angles. So the next step is toolpath and optimization. Right now, we just did the geometric design. So there are multiple stages for that. So first of all, the stop and starting planes for 3D printings are not always parallel. In fact, we try as much as possible to create a flat arch to enhance or improve the shear capacity of the system. So as a result, we ended up with certain cases that you would have local and global failure during the printing, and that depends on the angles by which you're cutting your structure. So that had to be optimized, and this is what we did. In the next step, we went through the geometry, which is basically optimized at a global level, and look at the local areas and basically optimize the location of the toolpath. And for your information, the geometries that we're dealing with are not possible to be printed using continuous printing. So we had to start and stop the print because the cross-sections are different for this anti-classic geometries, the spatial anti-classic geometry. So what we do is that we develop this graph that represents the relationship between groups of elements within that system. And then further down, we basically subdivide that graph that represents actually the constraints of the machine, proximity of the groups, to be able to continuously print all these elements. So as a result, you would end up with a diagram like this that allows you to complete the structure sequentially to be able to finish that complexity with minimum amount of material. As you see, it's just one layer of concrete. But this has been distributed in 3 dimensions to give geometric stiffness to the system. So we have to work with a material that is unknown in terms of the properties. Obviously, we do a lot of research in that field, and we work with our collaborators to do the load testing and compressive behavior, tensile behavior, deriving the modulus of elasticity for the material, using the test, and then use finite element models, discrete finite element models with, again, contact areas to understand how these systems would actually work and behave, and do the physical testing and validate that in order to develop a meaningful model that would actually very well represent the result of the work, right, in larger scale. Next stage, we move on to the prototyping, right? So we start with 10 scale. 1 to 10 scale. We started with clay printing because obviously, because of all the complexities that I mentioned, it was really important to make sure that we can print this using 3-axis desktop printer that was developed in the lab. So you see that these type of structures are actually possible to be assembled upside down, and you don't need any formwork. You can actually put the post-tensioning and then flip the structure depending on the scale. This is what we did, obviously. 10 scale is very small, and these are some of the results with clay. Then we moved on to the half a scale, which, for your information, half a scale is actually 5 meter span for the actual structure. So these are some of the results. Again, to control the precision, and this was the first time that we were doing, we used foam to make sure that all the pieces are aligned well, and we did not have a capability to flipping this because of the limitation of the lab. And yes, as you see, the segments are aligned with each other. The cable goes through everything. It's not grouted again, so you can actually take it off. This is the scene that the research team are basically post-tensioning the structure. It's just as for your information, yes. And for those of you, again, who are familiar with post-tensioning, in a common practice, they usually post-tension the entire structure, or every strand or every cable to 1500 megapascal. Here, we only post-tension it to 350, so it's not a lot of post-tensioning. It does not impose a lot of danger in terms of explosion. And this is the self-supporting structure. Some of the details of the close-up details, we use neoprene between the elements to, again, prevent from local stress concentration as a result of post-tensioning. Some shots. We did preliminary test. This is 1,000 kilogram on the structure. And then currently we're running a more extensive, rigorous load testing, 2-point bending test for half a scale. The next stage, thanks to our collaborator, Sika Group Switzerland, we're moving actually to 1-to-1 scale. So they're printing these prototypes in this scale, as you see. That's actually the human scale, as you see. The size of the components. And again, the entire argument is that how we can actually minimize the use of concrete. It looks bulky, but in fact, if you look at the cross-section, it's actually very minimal, right? So some of the images of the cross-section of concrete that has been folded in 3 dimensions to gain a stiffness, and some treatment afterwards to get them prepared. So what do we propose? We are proposing to build this structure in a composite configuration. So here, a wooden base is used to support the concrete beam, which is quite ironic because you've seen always the concrete 3D printed supporting a wood, but concrete is actually super lightweight that can supported by CLT. And we had other constraints for the site. So this is actually showing the full scale concrete that spans 12 meters. but the limitation of the site was that we could not exert a lot of force to the soil, and we had to distribute the self-weight of the structure using a little bit ductile material as CLT. This is the reason that we also went for CLT, and also it shows that how these type of technology in the future could be mixed up with carbon positive material to gain carbon neutrality, right? So some of the details of the final production. This is hopefully happening in May 2025 in Venice. And to just summarize the project impact, we reduce the concrete volume. We take advantage of the advances of concrete industry, which is post-tensioning. We mixed it up with a design that could actually minimize the use of concrete. We address the recyclability issue, which is the main thing about the embedded reinforcement within the concrete. The surface area of three-dimensional anti-clastic geometry could be taken advantage if we work with material scientists, which currently we do, to use a recipe that can absorb carbon. That would be also beneficial, so we could actually maximize the reduction. And obviously 3D printing concrete is actually an efficient way because it does not involve a lot of waste. You can replace these elements quite easily, and it's quite efficient compared to the conventional systems. So with that, I think I'll stop.
Thank you, Masoud. Thank you very much. And we now move back to timber. I welcome Fabian Scheurer. He is head of, and Moritz Niebler. Both of you are presenting. The WISDOME timber grid shell, which is flat packed and bent on site. And Fabian, we are almost now colleagues in Munich. You recently started at the across the street, at the Hochschule Munich, and both of you are parts of design to production, a well-known also part of the FABRICATE community company. So we're really keen on hearing about this project in Stockholm. Thank you. Yep.
Hello everyone, it's a pleasure to be here again. This is our 5th FABRICATE and we're really proud that we didn't miss any of those. We'll be presenting a real-life project, applied science if you like. My colleague Moritz basically was the one who did it. I'm just sort of presenting the view of the architects who can't be here today, more or less. So Johan Oskarsson and Jonas Elding say greetings, but they couldn't come from Stockholm to be on stage with us tonight. This is, if it's going, yes. This is WISDOME. WISDOME in Stockholm, the actual WISDOME is the geodesic sphere in the middle that you can see here, made from cross-laminated timber panels, hosting a screen for scientific projections. And it's covered by the actual topic of this talk, a 1,200 square meter timber grid shell, elevated on stilts, if you like, on columns on the side, which adds a little bit to the structural complexity of the thing. It's built from 5 crossing layers of curved beams with a cross-section of around 135 by 350 mil, changing slightly in width, because each beam itself is made from 5 lamellas of LVL timber panels. Only in the lowest beam, those 5 lamellas are glued together, and all the others are just stacked on top of each other, held together by shear dowels, also in timber that you can slightly see here, but there will be better views on that later, and a few screws. The building is an annex to the Stockholm Museum of Science and Technology, located in its courtyard, basically, a former parking lot. And it's connecting 2 existing buildings, and forms sort of as a hinge between those buildings and hosts the projection sphere and a few other things. And it's decked with wooden shingles. It was opened last December by the Swedish king. which we were very honored by. And after the king was there, also other people could go in. So this is the first picture with people actually in the structure there. Taking over sort of the part of the architects that couldn't be here today, the design started in 2018 when Elding Oscarsson Architects won the competition together with engineer Florian Kosche from Norway, an invited competition by Tekniska Museet, and the idea that they came up with is actually quite impressive, I think, because this backyard of the museum had a few sort of requirements that were hard to fulfill, because the buildings around are rather flat, so the new building shouldn't take all the light away. But nevertheless, it had to fit a 12-meter high projection dome in there. So the question was, on this plot that we have there in the midst of listed buildings, and opposite the royal gardens of the Swedish king on the island of Djurgården, where he's hunting deer, I've been told, or had been, how you put that in. And the idea, of course, is, okay, we need a dome, we need a little cafeteria, we need public space. We could put a sphere into a box, or we could put a sphere on top of a box, and basically what happened is they shrink wrapped the sphere into this timber grid-shell roof. And had, of course, discussions with the engineer, and were told it's working. But one big prerequisite of the project was the financing of this extension to the museum was sponsored by Stora Enso, big producer of timber products in Scandinavia, which meant that their materials had to be used, because if they wanted to sponsor the material, not the money. So basically on the menu are LVL on the left-hand side and CLT panels. So either very thin layers of timber glued together or thicker layers of timber glued together. And that proved to be more difficult than it actually seemed in the first place. So pandemia came in also, and in sort of 2020 the project got stuck at a point where they couldn't solve it. And they had developed also plan B by twisting the cross-section of the beams 90 degrees that you can see on the right-hand side, but still it didn't really go forward. And then Moritz is taking over.
Yeah, and then in 2021, Elding Oscarsson picked up again and wanted to push the project further. And so they didn't know actually how to go further, and they basically just asked a simple question to the good old Google and asked timber grid-shell. And a few projects turned up. So for example, the Centre Pompidou in Metz, the Ninebridge Golf Club in Jeju, the mosque in Cambridge, and the Swatch headquarters in Biel. And along these projects also, next slide, names popped up. So they just called the first name popping up, which was Blumer Lehmann from Switzerland, a timber contractor. And yeah, and they just had finished like 1.5 years before the Swatch headquarters. And Blumer Lehmann called their partners, which is Creation Holz Timber Engineers and SJB. Behind Creation Holz maybe is Hermann Blumer. Some maybe know is quite a old, well-known timber engineer. Sorry, yes. And they also called us and brought the whole team, which had quite some experience in all these projects you see in the back, which they did for over the last 15 years together and collaborated, and brought them to the table. And now there was quite some timber knowledge, grid-shell knowledge, and how to do these projects around the table, but there was a problem, because all of these past projects, they were made from glue-lam timber. So small bits of pieces, lamellas of wood glued together into a blank and then milled out on a large-scale CNC machine. But GLT, or like glue-lam, was this time not really on the menu, as Fabian said. So, and also this process would have not been in the budget and in the time frame, because it's quite a labor intense, time intense, and also expensive process to do. So, no glue lamp, so the challenge was up. How do we build a shallow 1,200 square meter roof grid-shell structure with LVL lamellas bent on site without glue? I mean, it's half true only, because LVL itself contains quite a bit of glue, but the lamellas in between them not glued together. So just holding them together by mechanical shear dowels and screws and threaded rods. So to do this, or like the process of what has been needed to do for this like applied research project was the whole thing needed to be planned in 3D with every little screw, and it had to be unrolled into the flat, because it needed to be milled out of flat sheet material with all the details, and then it got nested into sheet material, milled from these sheet material, standard LVL sheet material, and packed together and shipped on site. And then they were craned into place and bended in, and fixing them with just dowels and screws, basically. So as I mentioned before, none of the team members had really experience with it. So it was pretty quickly clear there were needed to get some insights into the project. So there was quickly decided we're going to have to build some demonstrators, some mock-ups. So the first two mock-ups built very quickly in the beginning of the project. So which was a technical mock-up, basically to test, does the material bend, does it go around the curve, and does it keep the shape? And also a design mock-up, how does it look? And the results were a bit not like super encouraging, because it was like there was quite some setbacks and it became clear there's quite a challenge. But nevertheless, the team said, okay, let's push this project and we go on with it. And so after it was contracted finally, then also a third mock-up was done, the process mock-up kind of, where after the further development of the detailing and the construction system, everything was tested basically, also the production chain and also the manufacturing with subcontractors to really bring all the supply chain in the mock-up on board already and test this whole process. And also, of course, if it comes together at the end. So at the end, as Fabian already mentioned at the beginning, we have 5 beam layers where the lowest is like laminated, like classically, and also acts kind of a false work for the rest of the timber of the segments bent on top. These roughly 3,000 individual lamellas were produced just in time, packed on stacks, and then shipped to Sweden. And they were held together by roughly 3,500 wooden dowels, but they were rationalized to 3 cross dowel types and 8 shear dowel types. And at the end, it worked. The installation went smoothly, with, to the extent, no bigger necessity for chainsaw was needed. And the topping out party was roughly a year before the Swedish king opened the project.
Just in time, yeah. So basically, something completely new to us to build a timber grid shell, not from CNC milled stiff beam parts in a way. But on the other hand, and this is where it comes back to where all the other timber grid shells happened actually, the process that has been developed over the past 15 years with the whole team that was involved there, including the engineers and the fabricator, worked the same way again. And there's a few important things that are sort of pushing this thing forward. One is architecture as a process over time, and in this case, it was a pretty high-speed project. We had altogether a little bit less than 6 years between the competition and the Swedish king at the end. But in the middle, there was basically just 13 months of planning, production, and installation, preceded by about 3 months of research in there. So altogether, after getting to know each other for a couple of weeks, the whole thing was done in 20 months, basically. And that means it starts with really blurry concepts in the beginning, and it has to end with crisp and sharp and ultra-precise fabrication data for all those 3,500 parts that need to come together. And if you look at building projects, typically, this is what happens. Yeah. You have the knowledge of the project rising over time, but you throw away all the digital information after every stage. Because, yeah, someone says, hey, let's build a new model. The latest after the conversion or the transition from the tender stage to the execution stage, typically the contractor looks at the models that he's getting from the design, dumps them, and starts to rebuild his own fabrication models due to them not being precise enough, not trustful enough, or other things. And exactly the same thing basically happened here again. We had to restart things after the design stage. The other interesting part, and that's sort of why I'm so happy to see this pre-stressed 3D printed concrete now, or post-tension, 3D printed components now, as architecture from our point of view is made from parts. So doing homogeneous things on site is sort of contrary to what we want to do, is getting complexity away from the building site and making things in the workshop as precise as possible. So in this case, we had about 3,000 lamella segments, and we had about 3,500 wooden dowels that had to be milled precisely on CNC machines. And of course, what you have is basically an explosion of information somewhere in the process. You start with simple design models, and somewhere in between, you have a couple of 10,000 screw holes to drill in there. And how do you do that? Of course, you all know the answer. You pull out whatever it is and do parametrics. So we have an undetailed model, and we turn it into a detailed model, not by modeling every screw hole, but by implying some little scripts and grasshoppers and whatever is there. So that's given, that's there, that's easy. But the more, or the bigger problem in there always is, in the end, you have a typical CNC machine that's producing within a couple of tenths of millimeter tolerance. And this is not only because it's standing in Switzerland at Bluma Lehmann, and the Swiss always have a fetish for precision and actually want to do tiny little watches. This is because the details need to work in the end. We have shear dowels in there that work on contact, and if they're sloppy and loose in there, they just don't work. So for the structural integrity of the thing, we need this precision. Otherwise, the machinery wouldn't be there that could do it. But that gives you the sort of headache of how to turn early design model with 5 millimeter tolerance into a crisp and sharp model with 5/10 of a millimeter tolerance. How do you do that? And this is where technology doesn't really help us yet. Yeah? So the trick where you push a button and then the blurry image gets sharper, like at CSI Miami, where you can then read the number plate, it's just not working really. Yeah, it's cinema. So we have to come up with different things there. And the last and the most important thing from our point of view is architecture is made of joints. If you have parts that need to come together, you need to think about the joints. And if you want to do that parametrically, you have to have a really systematic approach to doing that, because you cannot allow to forget any of those joints in there. So all the parts are individual, but they need to follow the same rules. And we have all the part types here in our models, in our digital model, in our parametrics, and the same amount of joint types on the other side. Yeah, so we need to stop talking about parts all the time. We need to start talking about joints also. So how do we do it? Quickly, because I'm over time already, I realize. If you want to do prefabrication, you have to discuss design for manufacture and assembly from the start. So you have to think about what's happening on site, because it doesn't make sense to fabricate things that cannot be assembled. And it doesn't make sense to design things that cannot be fabricated. And that means you have to drill deep from the very first stage there, but then resurface, because at the concept stage of the project, it doesn't make sense to put in all the drilling holes. You just need to be sure that it's working in the end. So this is what we're doing over the stages of the project, whatever the name, from left to right. And the other thing is, if you want to do parametrics, You cannot build one model that gets ever and ever more detailed, because if you need the model as an input for the parametrics, and then you throw it away, or you don't update it, you cannot backtrack ever. And if you make a mistake, and you will make mistakes, or someone's changing something here, you need to run the parametrics again with the model that was there in the first place. And this is why we're building a stack of models of different detailing on top of each other. And the very last slide, you have to have a parametric or systematic way of dealing with details. What we do is actually we're looking at all the components that are in the building, and we're making a matrix and say, hey, who's colliding with whom? And this is not bad. Collisions are fine, because where a collision is, there needs to be a joint. So from there, we create a joint list. And this is surprisingly something that's not really happening systematically in building up to now, and not in BIM at all, because BIM models don't even know joints. They just know parts. And that, from our point, is the sort of important message that we would like to discuss with you. Is we need to talk about interfaces and joints, both in the models and in the processes. Thank you very much, and to all the things in here.
Thank you, Fabian. I think we now all collect on our panel. There's no seat order. I think. Okay.
No. Then we.
Maybe.
Shall we move up?
Yeah.
Okay, move up.
Okay. So separate. Okay. Before we open questions to the stage, we will make a short internal discussion, because I did prepare some questions. We also had an opportunity to talk beforehand already. First, thank you for all of your nice, really nice presentations. All of your projects are very mature, and they already show that there's year-long research actually behind, and they are very sort of on a level where they almost go into practice, no? As Anna also said. So I want to start with a question picking up on this morning's presentation. I think we heard about design as a synthesizing complexity. No? And I think this maybe is, for instance, very beautifully reflected in a sentence by you, Anna. You wrote in your paper, the transformation of 3D concrete printing into a genuinely effective tool for reducing resources. So considering workforce, formwork, and concrete in construction demands a multidisciplinary approach that fuses architecture, material, and structure into a comprehensive fabrication method. No? So the results of your synthesization processes are, I mean, especially in the projects which are more mature, they're all already crystallization processes, and your name also even says it, no, Diamante, which is basically reflecting traces of your research of a very long sort of iterative process, also very specific design decision, no, they're all reflected in what we have seen here in all of your structures that you produce. So my question would be, to which extent do we need to expand this synthesization process? No, because now we have material, structure, all is kind of related in this process. But we have been hearing, and the discourse that goes into the direction that that's not enough. No, we need to synthesize also where does the material come from, where does the energy come from, and we need to kind of this needs to be taken into account. All of these factors need to be taken into account. So I would like to kind of ask your personal reflections on this matter, no? Of this expansion of complexity and the synthesization that is necessary in order to make the steps that are necessary to design for the climate that we are asked to. Yeah. Who wants to go first?
I can probably start as quick as possible. I think we need to get rid of a lot of complexity, and this is basically what rationalization sort of means also from my point of view. And this is sort of also because this is where my obsession with interfaces comes from, yeah, because I was trained as a computer scientist, which means I'm used to dealing with black boxes. Something goes in, something needs to come out, and I don't care what's in the middle as long as it works. Yeah, and this is sort of the definition of interface. And that can be in a process, and that can also be between two parts in a building. And that probably is something that we need to sort of look into more often again and say, hey, if everybody talks to everybody all the time, things don't move, or they tend to get stuck at one point. Sometimes you need to sort of a little bit compartmentalize processes and also constructions in a way that you can handle them still, because we have too complex things going on in those projects, oftentimes, I think.
Mm-hmm. So what you're saying is that the synthesization process is already rationalizing, is already simplifying to some extent?
Yeah, definitely. Yeah.
Masoud?
I think I tend to agree in certain respects with you, but I also disagree on the other aspects, because sometimes it's very difficult to you said that reducing complexities of the project.
Yeah.
Sometimes you deal with some phenomena within your project that it's quite complex. For instance, in our case, yes, dealing with tolerances, complexities of production, optimization, all these things, as architects and designers, we're used to that, right? Mm-hmm. So the computational package behind it, everything. But then when you deal with material properties, there's another realm of unexplored field that's just like, you design something you expect to work this way, but then you go into deeper to the subject of the matter, and then you realize that material does not support. Material is not what you're doing, or at least intending to do, and that becomes another additional piece of information that tend to change the design down the road. So I think that's very common in your case in the 3D printing, right? Yeah. So I think. Yes, it's great to reduce complexities, but in the meantime, in certain cases, it's impossible to reduce complexities.
Yeah, of course.
We have to embrace the complexities, and that's, I think, the next phase in our work, at least what we've been working on, is that how to deal with this material complexities, right?
Mm-hmm.
I mean, I think in our case, this not always talking to everybody else is probably more difficult. So we have this notion of co-design or like concurrent processes where we also based on the structures that we do and the requirements that they bring with them, we kind of need these overlapping dialogues and these concurrent information streams that we somehow need to manage, right? So I think this complexity to a certain extent is unavoidable, and we will have to learn to deal with it and embrace it to a certain degree. Yeah? So that's, or at least that's our approach with the fiber structures that we do.
Mm-hmm.
Yeah. In our case, I want to point out the design development from the stage of the demonstrator, where we worked with differentiated components based on functionality. So we had columns and slabs, to the current design where we have a more complex component, the V-shaped component that is basically the typology for the entire tower, and within this component that follows several rules, we start designing and we start to add variation to the small level of material ornamentation that creates every column unique.
Mm-hmm. No, I mean, I really like what you said, Masoud, to not mitigate, let's say, the complexity, you know, to really to embrace it and to also understand that there will not be this kind of optimal kind of solution space, no? But one proposal to kind of address these complexities, no? Because all of these projects, or literally everything we do, can only be addressing something, but there will be always open question, no? And maybe to take this a bit further, no? Also again to draw back to the discussions that we already had, is they are all iterations, no? And they are all, let's say, also very nicely shown in your project, Christoph, because you basically show this iteration from the glass fiber to the natural fiber, and now the resin that you want to replace now with a kind of bio-based resin. So they're all iterations. My question is this iterative process enough in the moment where we are kind of confronted with coming up with solution yesterday, the day before yesterday, and so on. No? Like this immediacy that we are also as a practice or as a community that is asked from us, no? To kind of be faster. Is this iterative process, is this enough? And or would you think we need to be even more radical in that sense? Yeah.
I'm not starting here because I'm doing the applied things.
No, that's actually a good point, because being radical without doing lots of iteration means taking a lot of risk.
Yeah.
And if you're doing a real project like the project that you showed, it's really difficult to take that amount of risk without doing all those iterations. I would love to actually hear from you. So what would be your?
No, it's absolutely true. I mean, this is sort of one step further on the way that we already went to get this real world project going. I mean, I think not only for me, it was a quite sobering keynote this morning, in a way that probably is not enough. Yeah, we need to start thinking differently about things completely. On the other hand, this is what we can do at the moment, and we were lucky to basically by accident end up in the timber corner, which has at least some green credibility. But still, it's not enough. Yeah. So the thing is, what can we do on top of it? And that really is taking the risks on the research side of things and come up with new ideas. Because I think on the applied side, it is typically iterative. Because it's hard to sort of have someone taking the risk to do something completely new at that scale directly. Yeah.
Any other thoughts, Christoph, Anna?
Yeah, I would agree. I mean, I also tried to show that in my presentation. So basically, that's what we have, right? So this is what we know, what we developed over the last years, and we try to build up on it and expand it and progress and be faster, be more effective, be more sustainable. Yeah? And I think it also or the project also shows that it works to a certain extent. I don't know if maybe it's not fast enough, but. I think it's definitely a way forward. Yeah.
Anna?
So I will
synthesizing.
I will try to address the question from coming from the opposite side, from working with concrete. I think it is very important to think of these processes as a way to increase the resolution of fabrication and be aware that every trace of material that we add within a structure has an important addition to what we are building, and be very aware of material optimization and of designing the parts in a way not only from the exterior part, but also looking deeper into the medium scale and micro scale of the component itself.
Yeah. I mean, I have one question noted down exactly to that topic. In fact, like this, how did I name it? Yeah, I think this question of material composite versus material assemblies, and this, the amount of complexity that goes into the components. So now you have this extremely optimized component. It serves all of the functions that you had taken in mind, and it's perfect for the situation. It's perfect for that building. But again, if you think of end-of-life use, I think you have addressed this with the post-tensioning, so material separability, which is already one step in that direction, but still, at the end of its life, you end up with a component that is hydrated, that has gone through a chemical stage, or that has been glued, or that has been cut, and there needs to be some sort of thinking towards what will happen with it. Again, the question is this: do we think far enough? Again, I think it was often talked about already that we have to take into account the whole cycle of the material regeneration and so on. Are there any, or what are your personal ideas as to how to address also these questions?
Maybe I'll just dive in. I think if you look at the design process today versus 10 years ago, the design process is becoming more complex because of all the parameters that you need to take into account to execute what you've basically planned for, but also the idea of the end-of-life scenario, right? The life cycle impact, the life cycle analysis. Everything right now, those are additional measures that we need to bring right now into design. And this is going to continue in the future. So the more people involved with those topics, the more it's going to be even more complex. But it's actually for a good thing, because then that brings this notion to us that we really think what is going to happen at the end of the life cycle. How do we design it to reach to that goal? And for me, I mean, one of the reasons that we're really pushing in this project that you saw as post-tension concrete, to do not involve any kind of reinforcement within the system that would be embedded. As much as possible, we try to avoid it just because of that reason. And that ended up being a little bit problematic if you want to compare it with the conventional systems or with the embedded reinforcement. So we have to do, in fact, lots of iterations, lots of design iterations to address that point, which adds to the process of really design to production, right?
I think an interesting point there is especially what we also wanted to push for a bit, like really when it comes to the interface between like two parts, because also like not only we design for like putting them together, but also then taking them apart again and maybe reusing these elements somewhere else, or like, which was also presented yesterday. So that's really, even this point then becomes more important further down the line. So you have really to discuss between different contractors or between different parties, planners, how do we put together two parts and how do we put them apart from each other again?
No, I mean, in my own reflections, I think Bob said it this morning that I have been also part of this community for a while, and I do agree that I think there is a shift in sort of being able to see the complexities of, or to embrace the more systematic approach. And it's probably true that we do, that our design processes do increasingly become complex due to the fact that we do need to, open up to all of these other factors that we have been or that have been looked at very compartmentalized, and where we are not allowed to kind of compartmentalizing them again. And I do think that, although it probably seems very kind of slow to some, but I do think that there is a major shift in that sense that we do understand the entanglement. Again, to pick up on a term that was used this morning, entanglement of building culture with the material culture, for instance, to kind of to really embrace that, and also to, with that entanglement and with that being able to handle the complexities, where digital tools may be very fundamental in being able to do so, hopefully will help us to address some of these major challenges that we have, that we are facing. So having said that, I would very much like to open up the questions to the audience. We have one here already.
Hi, thank you so much. So we now had a discussion about complexity and increased complexity. I think also we should discuss how we can decrease complexity. And with your examples with the grid shells, so now grid shell 2.0 and the old grid shells that you have been making, could you discuss a bit about complexity there, and if you were to choose the next grid shell, would that be with this other method or with the old method?
Well, actually, I would love to not do a grid shell again. Not because I don't like grid shells. We've done a few. It's all fine. But the actual next task for us would be to get this sort of rocket science approach of all these crazy curvy projects onto the road, and apply all those tricks that we think we've learned to more orthogonal buildings. And that proves to be really difficult, because we've tried and we've miserably failed. And mainly because yeah, it's difficult to realize where the complexities actually are. And we think we know how to build orthogonal things, but we probably don't really know yet how to build prefabricated orthogonal things out of timber so perfectly, and then where we can rationalize. And that sort of is the main keyword, I think, at that point. Because when we try to do, then of course someone stands up and says, no, we've been doing it for 25 years, it's actually working. Who are you to tell me? And this is different in the crazy curvy corner, yeah, because it's not gonna work. Yeah, someone needs to address it differently. But that's not happening in the orthogonal field at the moment too much, and I think we should address that and try to get out of the rocket science corner there. That would be my aim.
Something to add there maybe is grid shells are, at least geometrically, they may be complex, but typology-wise, they are not super complex.
Yeah.
You quite easily can understand the dependencies, kind of, but and therefore, like rectangular kind of buildings, the dependencies are much more complex than like in a grid shell structure. So, yeah, that's maybe just to add to this.
Yeah, thank you.
Thanks.
Thank you.
Yeah, Fabian, you were like already addressing the question that was burning on my, like in my head all the time. We have like all this incredible genius power of our minds, right? Like in following this keynote lecture today of Indy. Why is complexity for us still resulting in complex forms or complex fabrication processes, super elaborated, intricate interfaces, right? It's beautiful, but why can't we just put this mind into working on complex interdependencies, on social interactions in buildings, cities? It is because it is much harder to handle, right? I mean, you said it, a grid shell is easy topologically, but looking at portfolios of big real estate players, right, and telling them not to build new houses to increase their value, but reconsider not building stuff, but still increase their value by, I think this is where we need to be like in 3 years, right? Like we should not concentrate too much on like digging deeper in all these rocket science. I mean, it's amazing and it's important for sure. But we also need to use our intellect to grasp like real problems and enrich what is out there, like this 90% of buildings. We don't need another demonstrator which is a free form. I'm sorry because I really adore all of these projects, but it's like, yeah.
Yeah, get me a straight project.
Yeah, I want to have a straight project. Like the next revolution would be like a super boring. That's why, like, really, India. I don't know if he's still there. I was really impressed. Like, let's join the boring stuff, but answer complex and interesting questions, which are relevant for the society, not only for our bubble, right?
Yeah. Yeah. Nothing to add.
I would just argue that if this complexity does not happen in our exploration, then you would not be prepared to do a good job in simple cases. This kind of research is necessary for you to understand how to handle that, what would be the new approaches, how you can do things better by taking these radical approaches or radical actions in research. And then when you face other problems that might seem simpler, then you at least have that knowledge that you can utilize and develop better solutions. So I think this is quite valid for any other type of research, any other type of field of sciences, right? So you might ask why all these basic sciences scientists in the field of physics and astrology or even mathematics are doing all those complexities when we could solve many things easier or have formulation for many things, or simpler formulation for that. But the answer is that the result or what they discover in certain aspect might actually become applicable at some point somewhere else. So I agree with you. And I believe all these complexities that we are embracing is just for the hope of reaching to that simplicity, right? You cannot get to the simplicity without going that direction to understand all the parameters that are basically meaningful for your design. That's what we do.
Thank you. Yeah?
Question? Following up on that, I just wanted to ask, now I'm a student, so maybe it's a little utopian or activist or whatever. I hope to keep that throughout my life. But I don't know if this will be too naive, but I wanted to ask all of you, I know that you're willing, but as well, all the genius minds that are in the crowd, are you willing to set aside to some limit the research and the projects that you're working on that lead to rewards? And we all get an ego boost when we get accolades and we make things that are beautiful. But to thoroughly contribute to something that has an actual big enough, the biggest impact that you could make with the tools that you have, because yes, this knowledge is applicable to other fields, but people who are excellent at parametric design, generative design, have the potential to, in multidisciplinary collaborative processes with others, actively, not just inspiring, to optimize all the other fields in, just like AI, in parallel to AI, with AI, to speed these processes up. We're already late, so are you all willing? You don't have to answer now. It's just a question that I wanted to genuinely leave. I'm in strategic design. I have a background in bio-design, like I'm touching certain things, but I do not know, I can't even implement algorithms anymore in Grasshopper. I could basically before, and it's something that I'm thoroughly missing. So just from that standpoint, I think it's really relevant to actually, yeah, am I ending this, do you know?
Yeah. How are we in time? Do we have time for more questions?
Gone, so go on.
Yeah? I see here, 30 seconds. So, one question, here, in the back.
A lot over there.
Thank you. I have a similar question to the simplicity. So I really find the joineries really valuable. So I wanted to ask you if these joineries could be really like applied to normal housings and like the rest, like the not too complex buildings that we build all the time. And a small question also about non-organic like fibers, for example. Could we extended life of the chemical ones and actually in the long term reduce the carbon so by reusing or reassembling them? So would it be like making the life longer of the non-organic materials research like this course as well?
Christoph, that goes
yeah, so I didn't fully understand the question. It was about whether natural fibers can extend the life of existing building components?
So what I'm saying is actually like the like there is really a lot of interest in making organic fibers and organic materials, but non-organic materials, by reassembling them, could we, and more durable materials that are non-organic, and could we actually in the long term have less impact on the environment by just using the non-organic materials, just increasing their life cycle, lifetime?
That's a difficult question. I mean, of course, it's always beneficial to use to extend the lifetime of a building part, right? And to use it for an extended period of time. The question is also there's very, and there's also a challenge that we face with doing structures with plant fibers, that we have very little data for that. So we also don't know or know very little about the durability of those structures. So that's really an ongoing investigation in this field. So we're doing a lot of tests and to evaluate this, and then there's also the balance, right? When does it make sense to take this effort or to use a natural fiber component? And is there maybe an application where using a carbon fiber component that has a lot less material and is more efficient would be better. So this is kind of those difficult questions that we're facing, whether we try to determine what makes sense and when, in which case. And I think there is no universal answer to that. So that requires an individual assessment of this individual situation and load case and whatnot. Yeah.
Okay, one last. Seems to be eager to be questioned.
Okay, I'm going to try this. Following up on the last question a little bit and some of the conversation from this morning, I think I was struck by this set of talks because previously there was a lot of back and forth between, is this engineering, is this architecture, the architects, the engineers, how do we get these people to communicate? I don't think any of you actually told us if you're engineers or architects or fabricators. And I think in the presentations previously, and particularly this one, the engineering has become the architecture, that boundary is very intrinsic. I think myself, I've neither, but both. I'm one of these digital craft people, which has a very poor description, and I feel like I've been in these geometry groups, these specialist groups, that have actually owned the knowledge of both people because I can connect all of these different tools together. And when I think about, the conversations about shipping things internationally and how we're solving the world's problems, the discretization of the products that we're producing, I think, is one conversation to have. But I think the more tangible thing, particularly when you're talking about these impoverished communities, is the digital component and the digital tools. I think that was the first mention of BIM today, or this weekend. What of the digital tools are we missing, and how is the digital process, which was most evident, I think, in this series, what is missing in our tool set, and how do we kind of create and focus on this digital person, which I don't have a title for myself because I'm like an integrator, a digital, magician. What is this? I feel like we're missing this element that I feel like we've talked around. Can we discuss that piece?
Maybe we sort of are a little, or I myself feel I'm a little bit beyond the tool discussion in a way, because I think what we need to discuss to address the urgent matters that have been brought up this morning is on a higher level. And once we have new ideas how we address things and how we reorganize the processes and how we build, and as soon as we know that, then we can sort of ask for the tools to help us with that again. I'm really hesitant to break things down to a technology discussion all the time, because that is sort of, it seems like an easy way out sometimes. Yeah, I think we need to really talk about the processes, how we build, why we build, how we should build differently to have sort of different structures for different life cycles that can be taken apart, rearranged, whatsoever. And there is, of course, a lot of tools, also digital tools, that can help us with, but the problem is we're lacking ideas for the things that we need the tools for at the moment, I feel a little bit.
Great, thank you so much. I think that was a nice closing statement. We can continue the discussions in the break, and I think now you will take over the moderation. Thank you so much. A big applause for that.